why is A times quantity B plus C equal to AB plus AC true? You may recognize this as the distributive law. So for this one, it's helpful to draw the following picture. Now notice the left side. Let's deal with this side first. A times quantity B plus C. Well, look, B plus C is in parentheses. So let's focus on what's in parentheses first due to the order of operations. B plus C, well, plus, recall, was about gluing together sticks end to end. So here's a stick of length B right there. And then right there is where, right at that, where the mouse is, let me kind of circle right there, that will glue on a stick of length C right there. So then all the way across here is B plus C. And then that stick, well, times A, remember for multiplication, we need a rectangle where, A could represent the height of the rectangle, and then this B plus C, well, that's this all the way across. So this left side right here, A times quantity B plus C, is represented by this entire rectangle, these four corners, that corner to here, there, there. The whole thing, though, with these two regions is because of where the B plus C is, right where that gluing occurs, we can draw this line down, which isn't going to change the area. And we can talk about this area a new way, right? So this, first of all, let's just make sure that this big rectangle, it has a width of B plus C, adding is gluing sticks. The big rectangle has a height A. So the area of this big rectangle, all of what's highlighted in yellow, um, the area is height times width, so it's A times quantity B plus C. However, this big rectangle that was shown in yellow here occupies the same space as two smaller rectangles, the tan rectangle and the blue rectangle. And the smaller rectangle to the left has area A times B because this rectangle has a height of A and a width of B. The smaller rectangle, I mean smaller as in it's big, but not as big as the huge yellow rectangle we saw. So this smaller rectangle on the right has area A times C. Look, the height is A. This same height A applies over here. And then the width of this rectangle is C. So the two separate regions, they don't overlap. When we look at the total area, it's AB, this, plus that, AC. So AB plus AC. So here's the thing. This entire region, which was in yellow, when we looked at it as one whole huge rectangle, it was A times quantity B plus C, but that same region, we could account for the area as two smaller pieces, AB plus AC. So we've accounted the same region, its area in two different looking ways, and so this is why we have now a generic argument that A times quantity B plus C equals AB plus AC. I mean generic in that we didn't plug in any numbers here. So here's a summary of what happened. I mean, the previous slide shows some words as we were working through this, but the key thing of this argument is this picture that you see right here. The point again is that the area of the big rectangle is A times quantity B plus C, and if you look at the two smaller rectangles here, those two occupy the same put together as the big rectangle, and these smaller rectangles have areas A, B, and AC, and we added those together. Now, with all of this summarized up at the top here, some comments. The geometric interpretations of both addition and multiplication occur. First, the addition right here in B plus C. Multiplication, kind of all over the place, where there's A times that longer stick. And over here on the right side, there was A times B and A times C. So a lot of things are happening, lots of geometric interpretation. This geometric explanation is the only one accepted as an explanation for quizzes and tests. Sometimes looking at this formula, and people say it's true because it distributes. And by it, I think they mean A. So A distributes. Or they'll say distributive law or distributive rule as an explanation for why this formula is true. And that is not going to earn credit. The point, well, you might say, why not? And the point is that's saying it distributes because it distributes. Similarly, drawing some curved arrows. So what I mean is people will often take this A that's up here and draw a little curved arrow down this way, and then another curved arrow to the C. That doesn't earn credit. Those arrow drawings are really attempting to be the same as just saying, hey, A distributes. And why not? If these kinds of arguments worked that said it distributes or A distributes or drawing these curved arrows, then why not do this here? That same mode of thinking would be a justification on this false formula. But keep in mind, we already saw this formula is false. So how could this formula down here ultimately is false, but then what business do we have saying, oh, well, this formula is true because n distributes or it distributes, right? it doesn't. We saw by plugging in numbers that it doesn't. Sometimes people want to argue that this formula is true. Again, it's not, but people want to argue it's true by drawing an arrow from n to the x and then sort of a curved arrow from the n to the y. And that also doesn't, if people are going to draw those curved arrows here, and that's not good reasoning, why should that work over here, right? Why should that be allowed here and not allowed here? People confuse themselves into convincing themselves, I guess, that both of these formulas would be true by drawing little arrows that are curved or by saying it distributes. We can't have this kind of thing where the same line of thinking makes one formula true and another formula true when in fact one formula is true and another is false. We just can't trust that line of reasoning. So that's why we're doing this using the geometric interpretations of addition and multiplication instead. It's something that works, and that same argument wouldn't even apply over here because we haven't described a geometric interpretation of this exponent. Okay, so just to clarify again, we have this, which is called the distributive law, which is true, and this is I don't even call it the distributive law, it's some false version of the distributive law that people tend to think this is true because of how much it looks like this. But the key thing is there's a multiplication on the outside and there's a plus on the inside. Over here, yeah, there's a plus on the inside the parentheses, but this is not a multiplication, there's an exponent. So we did show earlier that this false formula is false by plugging in numbers, trying to argue that A distributes but N doesn't distribute. It doesn't, just in those words, just saying, oh, A distributes but N doesn't. That doesn't explain why one works and one doesn't. It's trying to say this works because it does and that doesn't work because it doesn't. That's not really an explanation, right? So we need something a little deeper than that. So for the false formulas, to emphasize this, always plug in numbers for the variables. To show that this here is true, the only explanation that's going to earn credit is the geometric figure, the correct and relevant geometric figure. Trying to say that this formula is true by plugging in numbers, for instance, writing 2 times quantity 3 plus 4 equals 2 times 3 plus 2 times 4, or similar, and simplifying one side or the other, that's not going to earn credit because plugging in numbers, it wouldn't show that this formula is true for all numbers. Now, you may be asked to show that this distributive law is true even if it appears with different variables. So don't memorize this just using the letters A, B, C. Maybe it'll say x times quantity y plus z equals xy plus xz. If so, you should draw a relevant picture. That picture should have the variables x, y, and z appear. Okay, so A times quantity B plus C equals AB plus AC. That's a true formula. Now what? So then turning what you have that looks like the left into this on the right, AB plus AC, it's called distributing. And then going backwards, if you have something that looks like this, A times B plus A, meaning the same thing, times a new thing called C, turning that into A times quantity B plus C, that's called factoring. Let's take a look at another example. Why is quantity P plus Q times quantity R plus S equal to PR plus PS plus QR plus QS? True? Well, let's draw a picture. So P plus Q, times R plus S. So this times, if we just sort of step back to interpret and see what's going on, to analyze, there's a multiplication, and that multiplication is the area of rectangles. So there's a P plus Q. Well, plus is gluing together sticks. So there's a stick of length P glued to a stick of length Q. So then all the way from this top left corner to the bottom left corner, that's P plus Q. And then same deal, R plus S. Well, a stick of length R glued to a stick of length S. So from the top left corner to the top right corner, that's a stick of length R plus S. So because we have a height P plus Q and we have a width R plus S, the entire area, that is all 4 regions here, all put together, all of what you see in blue, that area is P plus Q times R plus S. Now, the large rectangle is also split up as 4 smaller rectangles, right? So there's this upper left rectangle. It's of these smaller rectangles, it's the largest of them, but this has a height P and width R, so that area is PR. You also see a PS in the upper right, a QR in the lower left, and a QS in the lower right. And we add this large region, thought of as one big region, it looks like this here, P plus Q times R plus S. But when we split up this region into 4 smaller pieces, the 4 smaller pieces are each individually PR, PS, QR, QS, and we have to add those together. It's the same region. can be accounted for two different ways. We're just doing the bookkeeping in two different ways. Just to clarify some things, we showed that this formula here is true. It's called FOIL for some folks because if you look at what's happening, you have the first times the outside. So you have the first thing P and the first thing in the next set of parentheses R multiplied together. That's PR. The outside. So the first thing, the outside thing. You get to pick one thing from each set of parentheses. So the outside one, so P, and then on the outside here is S, so that's PS. The inside, so Q times R, there it is. And then now if you pick the last thing from each set of parentheses, you have Q and you have S, so Q times S. Now the only explanation for why this formula is true is a picture, and the correct or relevant picture. Plugging in numbers again will not earn points. Saying that this formula is true because of FOIL will not earn points. That's saying FOIL works because FOIL. Wait, that's circular reasoning, right? Now, just to talk about how this formula applies when something that looks like this with its two sets of parentheses and the plus signs is replaced with this over here, which has three plus signs. We call this foiling, or we call this expanding. When you go in reverse, when something that looks like this, PR plus PS plus QR plus QS, is replaced with something that looks like that, then we call that factoring. So now let's take a step back even further and look at this thing we called the distributive law. We already showed that this was true geometrically. Now we can use it. Now that we know it's true, now that we can trust it, we can use it, or to use some other words, we can apply it. So think about this formula right here as a template or a model. And what I tried to do here was use some color coding to help. So the A's you'll see are all in a yellow background, the B's are in blue background, and the C's are in a pink background. The point is you can turn something that looks like one side into the other side. And I use the word format here because we can replace the A with any expression. And same deal in reverse. If you have AB plus AC, in other words, if you have a plus sign, and then before the plus sign, you see a thing. Now, it's represented by an A here, but it could be something else. But then after the plus sign, you see that same thing. And these same things, the A here and the A there, are being multiplied by a thing that we're calling B and a thing that we're calling C. You can factor, and you can factor out an A, draw a new set of parentheses, and have B plus C inside the parentheses. All true formulas are like this. You can use them backwards if you want to call this AB plus AC turning into A times quantity B plus C backwards. You can call that backwards in quotes. But let's just look at some examples. So you're probably very familiar with the distributive law, but it's important to think about not just distributing every time you encounter it on its own, but because of what the things we're about to look at, it's important to think about the examples we're seeing as being connected to this formula, as really applying this formula. So for instance, 5 times quantity x plus z squared can turn into 5x plus 5z squared. So take a look here. In the formula up here, a gets replaced with 5, and that's everywhere, right? So the yellow A, there's one yellow A on the left, there's two yellow A's on the right. Those get replaced with 5 in yellow once on the left, and then after the word into, you'll see two yellow 5s. B gets replaced with x everywhere, and C gets replaced with z squared everywhere. Just for another example, just a slight modification of the previous example. In fact, instead of 5s to replace the A's, now there's m's replacing the A's. So you can turn m times quantity x plus z squared into mx plus mz squared. You can turn, and this gets even messier, you can turn m times quantity ac squared plus z squared into mac squared plus mz squared. You'll notice that right here, what's in blue, ac squared, that is what is replacing the b up in the formula. So this looks a little strange. Yes, I get it, because there's an a over here in yellow, and that's the a in the formula. The a in the formula is represented by m in this example, and the b in the formula is replaced by ac squared in this example. So the a in this, let's call this the problem. The a in the problem is not the a in the formula. You can also go in reverse, right? So if you took what I copied what was up here, 5x plus 5z squared, you can turn that into 5 times quantity x plus z squared. and you can turn mx plus mz squared into m times quantity x plus z squared, and so on. Right? So this, I want you to think often, these, especially these these, not the last three items on this slide, but the three previous, people tend to just distribute without thinking about or connecting it back to the formula, the distributive law. And I get that you do this because maybe it's so autopilot and you feel comfortable with it. It's just in just a day's time, in a week's time, we're going to see a number of other formulas that may be less familiar, and I want to connect a process that you feel very comfortable with in a framework that's going to work in general.